Okay, so we have made it to Monday, a real Monday. Woohoo! Welcome to a real Monday. So today we're going to talk about a bunch of stuff today. So homework assignment 3 was due. Very good job so far. What I've seen so far, it's been very good. There were many fewer requests for extensions, so that means that either you got scared of me and didn't want to ask for an extension, or you finished it. Hopefully it's the latter. And I'll have a couple more comments about homework 3 in a few minutes. Homework 4 has been posted. I did extend the deadline a couple of days. So it's the deadline is now Friday, like a week from this Friday, instead of a week from this Wednesday. So I gave you a couple extra days. But I'll say it again, start early, please. The earlier you start, the easier it is to get done early. What I was thinking of doing was making the deadline, keeping the deadline Wednesday, and then just giving everybody a deadline of Friday, like on Wednesday. And then everybody could be like, whew. But I felt a little weird about doing that. So deadline's Friday, a week from Friday. Okay? And I'll talk a little bit more about the homework 4 as well. And then today there's two kind of heavy-duty things we have to talk about. We have to talk about these things called copy constructors and assignment overload functions, both of which are a little hard to wrap your head around. They're not, in the end, they're not very difficult, and they serve a relatively easy to understand purpose. But some people get all wrapped up about, like, oh my gosh, I don't understand these other functions. Okay? So we'll talk about those, but it does take a little bit of time. We have to dig into some code to see what's going. And then, remember how I said when we started talking about trees, binary search trees, that they really only work well if they are relatively well balanced, right? So today we're going to talk about a particular type of balanced tree, and we'll get most of the way through that, depending on how many questions you guys have. We'll get most of the way through that. If we don't quite finish it up, then we'll finish it up on Wednesday. Questions before we get going? OK. So Unix tip of the day. So I think I mentioned this the other day. There is a program. Remember, you have a tree that you can use to model your directory structure. And there is a program called tree in the Linux system. So if you go over and let's say you are in the assignments directory of public HTML, public_HTML from comp15, you could do just an ls, and that's kind of boring. Gives you all the files, right? Gives you all the files. But you could run this tree program, which is really cool. It actually gives you a little graphical ASCII representation of what's in every folder. So that's kind of neat, right? You can actually see all the different files, and notice it's exactly like the one we talked about in class, where homework 1, for instance, the homework 1 folder has files folder and a homework1.zip file, and the files folder has all these other files in them. So it's just a tree, right? You can model it exactly like a tree. And the same is true for the other ones. OK, so if you want to play around with that, kind of fun to see a graphical representation of your directory. OK? All right. That's that. It does come with a bunch of different options. For instance, if you want to ignore some directories, basically, if you don't want to print out all the recursive directories, you can actually do -I, and it will ignore those directories. The little or sign means ignore that one. If it's that one, or if it's that one, ignore it, basically. OK? Questions on that? All right. So on homework 3, so many fewer memory leaks. Good job. I think you guys are getting a feel for memory management a little bit more, right? You have to clean up your program when you get to the destructor. And here's the deal. How many people, when I sent that other email on Piazza that said I added 2 tests, how many people had to resubmit and change some stuff? Don't be shy. Yeah. So what does that mean about you? Not in a bad way. What does it mean? Yeah? We're depending on the provide test. You're relying on the provide tests. Or not only that, you're not doing your own testing. right? So the functions that I ended up forgetting to test, and by the way, you should anonymously thank the person that came in and came into my office and found that and said to me, you better not like just test this on the final or on the after we get all done, because that would be mean. And I said, OK, that's mean. But anyway, yeah, you need to do that. And here's my concern, right? One of my concerns about this class is that sometimes I feel like we almost give you a little bit too much like stuff, right? We only give you we give you all these like provide tests and things, and I worry that you're relying on those, and some people are like providing like 30 times, right? I am limiting homework 4 to 20 provides total, which should be plenty, right? But still, what did you get in Cop 11? Like 3? But I think the point is you need to be writing your own tests to test some of these things, because in real life, if you ever write a program that somebody else uses, they're not going to give you a bunch of tests and let you check all those before they do it, right? You definitely don't want your users to find bugs and emailing and say, why is this function that we thought was going to be perfectly fine, why is it broken? Oh, I forgot to test that. No, that's not, although some companies seem to do that all the time. But oh well. You don't want to do that. So I do want you guys to be writing your own tests. And you've got lots and lots of examples. So please keep that in mind. Now, a bunch of people, and this was all over Piazza, right? We're trying to set two queues equal to each other. I mentioned this a couple weeks, like last week, but a bunch of people still tried to do that. And you can't do that. And we will talk about why you can't do that later on in class. We have to discuss these things called copy constructors and assignment overloads, because that's how you get around the idea of not being able to set queues equal to each other, for example. Right? You can do it, but you need to know what's going on when you do that. Okay? The compiler doesn't necessarily do what you think it's going to do or what you hope it's going to do. It does what it knows, which is very rudimentary. Okay? All right, so we'll talk about that. All right, homework 4. Homework 4 is pretty straightforward. Okay? In other words, all we're asking you to do for this homework assignment is implement a binary search tree. Okay? You need to implement the functions we talked about the other day. You need to implement the insert and the min element and the max element and the remove, right? You have to do all those parts of a tree, right? And which one's the hardest one? Remove, right? We spent some time thinking about that hard one. And you're going to have to implement that. Okay? So this assignment is very straightforward, but because you have to do everything recursively, and recursive functions are generally harder to debug in kind of the general sense, number one. And number two, because there are lots of corner cases, like lots of corner cases here, right? I mean, the remove function has so many corner cases. First of all, you've got 3 different situations. No children, 1 child, 2 children, right? Then you have to worry about whether it's the root or not. Then you have to, so there's lots of little corner cases. So there will be a lot of code in this, but it's not like the idea. You don't have to come up with you don't have to scratch your head and go, what does he mean when a student drops a course and then gets added when the capacity goes up? And no, all the logic is just in implementing this binary search tree. Okay? But I guarantee you'll be better at recursive functions, and you will understand binary search trees all throughout by the time you get done with this. Okay? Questions on that? You'll actually be, the destructor is tricky in a tree, because you have to go to the tree and you have to delete all the nodes in it, which means you have to walk through the entire tree. Today's lab and tomorrow's lab, you'll be practicing exactly that. So keep in mind, in fact, you'll be writing a destructor for the lab today that's almost identical to the one you'll write for the tree. So keep that in mind. You're going to get a little practice. Okay? Questions on this? It is posted. It is due next Friday. A week from Friday, yeah.
So is the remove function with no argument?
No, I just put the remove there to show that it's a function. Yeah. Other questions? OK. All right. So one other thing about this homework, now that I think about it. So this was so cool when I found this last semester. Somebody wrote a little function to take a tree and print it out in little ASCII art, right? Which is kind of cool when you think about it, right? So this is actually a tree. Notice it's a binary search tree. 5 is the root. 4 is to the left. 8, 7, 6, 9. So it actually prints it out for you. So most of the tests for this homework assignment will print out a little sample tree so you can actually see whether, like you can visually see if your tree is working, which is kind of cool. A couple things about this. It does the best it can. Sometimes it doesn't put everything perfectly. Like it puts a little underscore before the 7, which doesn't mean anything. It just means it's trying to get it like situated out. It's actually much more difficult than you'd think to get a tree to print out properly, because you have to do it in level order, and you have to make it wide enough so that everybody fits. I mean, what if you had a tree that looked like this? Let's say it was, let's see if I can do this right. Let's say it was, I don't know, 100, and then this way was 50, and this way was 150, and then this went 60, 70, 80, 90, and this one went 140, 130, 120. Notice how it crosses over, right? Well, it's hard to figure out if that's going to happen unless you look through the whole tree. So anyway, whoever wrote this did a really good job with it, and it prints out kind of nice. The big trees, there is one question which tests like it just throws like thousands of nodes into your tree. It's going to be impossible to read this one. It still prints out, but it's impossible to read it unless you copy the whole thing and then throw it into a like text editor with no line breaks. It will work, but it's still hard to look. Think about how big this would get if there were 5,000 nodes in there. I mean, it would be all the way across the board, right? Just trying to like fit everybody in. So not so efficient for the big ones, but still kind of neat when it works. Okay. Asterisks. For this assignment, you do have to do duplicates. And what an asterisk means, there is a duplicate in there. OK, that's another corner case in some cases, right? You've got, in this case, there's at least 2 5s. In this case, there's at least 2 8s. And you keep track of exactly how many in the code itself. Yes?
I was just going to ask,
yeah.
How do we keep track if we have multiple asterisks or something?
There's only going to be one asterisk, and it's going to be for each node. Each node will have a count associated with it. Yeah. Question? No. OK. All right. Any other questions on this? OK. So in C++, now we're going to shift gears a little bit and talk about what we call the big 3. Hopefully you read about this if you've been doing some of the readings. The big 3 in C++ are the destructor, this thing called the copy constructor, and this thing called the assignment overload, otherwise known as operator equals. Okay, it sounds like a code name or something, but operator equals. And these are, in the big picture, C++ specific things. Some other languages have them, but like Java, no need. Well, you can't do a lot of this stuff. You can create a copy constructor in Java, which you have to do. But otherwise, there's no destructor and no overload here. And some other languages have similar things. But for the most part, this is a C++ thing. Well, because we're learning C++ and because people get all confused when they try to set things equal to each other, you have to learn this stuff. In the homework, you will have to create at least an assignment overload for your trees. OK, so let's dig in. We already know about the destructor. It cleans up your resources for you. At the end of your class, if anything that you used new on still remains, you have to use delete in whatever the structure it is. OK? The copy constructor creates a new copy of some object. So you have an object, and then you say, here's another object, or I'm going to create a new object that is a copy of that. Here's how you might do that in C++. In terms of like the declaration of the thing. Let's say it was a Q. QA, we'll call it. OK, and then you do stuff with QA. And if you then say QB gets A, before I call this function, does B exist? No. In the process of creating B, the copy constructor is called because it knows it's going to make a copy of A and turn it into B. There's another way to write this too. You could say this, QUEUE B parentheses A. This is another C++ specific thing. This says create a B variable, that is a Q, and make it a copy of A. That's what it means. OK? And you might not have ever seen that way of doing it, but that's what it means. Okay? And this actually looks a lot like what the copy constructor looks like, as it turns out. OK, yeah? That's a good question. If we do this, so Nathan, you're stealing my thunder a little bit, which is fine. If you do this, if you say QB semicolon, now there's two Q's that exist, A and B. OK? And if you then say B gets A, without doing something else, this will fail. And we'll see why in a few minutes. But what really should happen is the operator equals overload should get called. Basically, the compiler says, oh, this is an equals sign. This is gets. Do I have a function that the user defined for this when there's a Q here and a Q here? And the answer is hopefully, because we will create one, and then it will do a proper copy of A into B. OK? This stuff takes a little time to get your head wrapped around. So we'll go through the details here in a minute. But that's the idea. Copy constructor, you don't have the new one yet. You're about to create it. Assignment overload, you've already got one. Make that one into a copy of some other one. OK? All right. So here's some code. All right. Let's look at what this code does. I'll do the top part, and then I'm going to ask you to tell me what it prints out. This is an int cell class. It's a stupid class. I'll tell you that right now. But what it does is it has a private variable, which is a pointer to an int. You say, why would you ever make a pointer to one int? Well, you could think of this as an array of pointer. And in fact, it's going to be a pointer to one int, which means it's an array of how many? 1. Right? So it really is an array of 1, but really it's just an integer. Up here, I've put the other code. To fit this on the screen, I've had to compress it. So this is a little bit obfuscated. Right? But take a look at this. Basically, this says, if you don't give it a value, make the value 0. This is another C++ thing. You don't need to worry about the details. But then it says, OK, the stored value, which is our private variable, gets a new int with the initial value. In other words, create a box called stored value, or that stored value can point to that is an integer. OK, that's all it's doing. Then you've got a couple other functions. You've got getValue, which returns what's stored in that box. And then you've got setValue, which sets what's in that box. OK, let's do an example. If I say int cell 3, and I say something like, well, actually, let's do it this way. Int cell A 3. OK, that creates an int cell with the value 3, which means that there is a box here. And actually, sorry, I lied again. It should be, oh no, that'll work. Yeah, this creates an int cell called A, and has this stored value pointer, which points to some box that it got, basically an array of 1 that it got from the memory system, and it puts 3 in that box. OK, that's what that does. All right, and then get value and set value. OK. So here's what I'm going to do. I'm going to create this A2 business up here. Then I'm going to call this. I'm going to say int cell BA, which gives me a copy of A and calls it B. And then I'm going to do int cell C. And then I'm going to say C gets B. And then I'm going to do A.setValue4. And then I'm going to print everybody out. Here's what I want you to do. Take about 3 or 4 minutes, talk to your neighbors, and tell me what this is going to print out. OK, in this form. And I'll start writing some stuff on the board. I could rewrite this. If you guys are confused about this line, I could rewrite this like this. Int cell B gets A. Figure it out, Erica? Working on it? Okay. Okay, who has an idea of who has a guess on what's going to happen? Did I give you enough time? Yeah, who has a guess? What do you think?
Hang on a second, I just need to. So it would start by printing 2.
Okay.
New line.
Okay.
Then it would, wait,
So it's first printing A.
and then it would try to print B, but B doesn't have a point. B's pointer doesn't point to an integer, so it's probably segfault.
So we're going to question mark segfault. Okay.
And then if it lasts through that, it would question mark again.
Another question mark. Okay, that's an idea. Who has another idea? Yeah.
422.
422. Okay, that's an idea. Okay, how about something else? Yeah. 444.
Sorry, mine should be 4.
You're,
Not 2.
oh, okay. Sorry, you didn't read. Okay, that should be 4.
Set value.
Okay. 4 question mark question mark 422 and 444. How about somebody else? Yes, Fury.
4-2.
4-2, who knows? OK. All right, that's a good idea. So let's walk through what's really happening down under the covers. OK? All right. I already drew this one on the board. It creates a little bar. It gets a piece of memory from the memory system to put the A's stored value pointer, like it puts says set stored value for A to point to the 2 or the box, and it puts 2 in it. OK. When it does int cell B of A, what it does, OK, is it says, OK, I need to create this B stored value. OK, and I need to copy everything in B. Creates B, and it says I need to copy everything in B exactly from A. So what happens is B stored value, because it copies the pointer, it says now B's stored value points to here. That's actually what happens. OK? And then we create int cell C. So what it does is it says C, and there's a stored value. OK? And because when you do this, this is the default value. So it creates a little box. It asks for a piece of memory from the memory system, gets the box, points the stored value to be there, and then sets it to 0. OK? Then it says C gets B. So when you get, there we go. C gets B. So what that does is it says, OK, if C gets B, then everything that C has in its variables gets copied from B. So stored value now does what? Points to here again. First of all, what have we done to this 0 down here? What's that called? A memory leak is what it's called, right? You now have a memory leak here, but that's OK. We're not running valgrind on this, but we could. And it would say, hey, some piece of memory is left over and has no idea how to get to it, et cetera, right? So that's what would happen there. And so we've got that. And then when it gets to here, it says a.setValue4. What does that change? Changes the box to be 4. And then now when we print everybody out, what does everybody print? 4, 4, 4. So this is what prints out. Probably not what you were necessarily hoping it would do. Given this code, you basically are saying C gets B, but I don't want them to both point to the same array or location, right? So this is what ends up printing. Now, let's fix this. OK? We have to make it so that this garbage doesn't happen. Everybody gets their own box, and everybody's box is like for their own values, right? So we have to change some things. OK? All right. So let's do that. This is where the copy constructor comes into play, and the other thing. OK, let's see. There we go. That's the actual output. Question?
Why exactly is stored value a pointer the way you declared it?
To demonstrate this problem. I did it.
Why does that declaration make it a pointer?
Why does this make it a pointer?
In the stored value it would be.
Well, this is a pointer because it's a private variable that is a pointer.
Oh, you did.
So this is a private variable called stored value, which is a pointer to an int. Basically, an int array that we're only going to allow to have a size of 1. OK? Yeah. OK. OK. Question?
So we didn't have the private variable as a pointer, was that just not happening?
If it was a, OK, first of all, if it was not a pointer, if it just said int stored value.
Yeah.
OK, if it did say int stored value, first of all, you couldn't do this. That wouldn't work. You would just say stored value gets initial value. And then down here, you'd return stored value. And here, you'd just say stored value gets x. And it would work fine. This is what happens in, say, when you set a student equal to a student. That's actually OK. When you say student A gets student B in the Q, like in the ISIS course thing, that works fine. Because there are no pointers in there. If you'll notice, there's just a string, which, by the way, has a copy constructor built in, and a Boolean, which is just a value that can be copied. So C++ knows the following. When it tries to make copies, it will say, what are my variables, public and private? Just copy them. So when it copies stored value, what is stored value? It's a pointer, meaning it's this big number that points to an address. So it copies that address to the new one. That's by default what it does. OK, so by default, you get this behavior. OK. So let's change this. Now, this is a little bit more code, but let's see what's going on here. Don't give me that look. It's good. It's going to be all right. Don't worry. OK, this one's called int cell fixed. OK, in other words, same idea, but I've fixed it. OK, here's what's going on. This has not changed. This is exactly the same. But now we have a couple more functions in here. We have this thing called a copy constructor. The copy constructor works when you do not have the value that's getting copied into yet. It has not been created yet. It's a constructor. How do you know it's a constructor? Because it doesn't have any return value. And in C++, that's a constructor. And by the way, it's called the name of the class. So we know it's a constructor. OK? And it's a constructor that takes what? Well, it takes an int cell fixed. And it actually takes a reference to an int cell fixed. We learned about this in lab last week. It takes a reference to an int cell fixed. And it says, don't change it. Right? It says, you are not allowed to change it. Here's what it looks like in practice. OK? If you have an int cell fixed A, OK, and you then say, I'll abbreviate, int cell fixed B A. Notice that this actually looks exactly like the copy constructor declaration. It is creating an int cell fixed with an int cell fixed that's already created being passed in. Does that make sense? Yeah.
53 ampersand A because you're passing in the address?
Nope, you're not passing in the address. This is a reference, which is not the address. That is a reference, which we learned about in lab, which means you get to use the original. The reason we put const on there is because if you're creating a new B, you don't want to change A. And you want the compiler to say, hey, you can't change A. If you tried to change A in this function, the compiler would say, sorry, that's an error. OK? That's why we have the const. And the reference is there so that you get access to all the private bits that you need. OK? So now, this says call the copy constructor. In the copy constructor, let's see what happens. Well, the copy constructor says stored value is new int. Because right now, B does not yet exist, so we'd better create a little box for it. And we'd better set B's stored value to point to that new box we just got with the new value, or with the new keyword. OK? And then it says, guess what? Copy the value that is at stored value. In other words, dereference the stored value from source, and I'll explain what that means in a second, and store it in B. source here, notice it's just like any other parameter. What's the parameter of this function? A, right? A is the parameter we're passing into this function. Therefore, A is what's called the source up here. It's just a variable name. It's called source. So source.storedValue is A's stored value. And by doing the star there, you're saying, give me the actual value, not the address. Give me the value that's at what this pointer is pointing at. OK? So that's here. And then you've done that. So in this case, you've created the box for B. You've asked for the box from memory. You've asked for the memory from the memory system. And then you've said, set my stored value for B to point to that. That's what that new statement does right there. And then you say, grab me the value from A and put it in my stored value. 4 goes in here. Well, let's say it was 2. That was what it started with, right? 2 and 2. Whoops. OK? Questions on that? Pretty straightforward what that one does. Now, this other one is interesting. This right here is called the overload of the equals operator. Now what that means is, and you can actually overload almost any operator in C++. You can overload the brackets. Like let's say you were trying to multiply, or you can overload the asterisk to multiply. Let's say you had a function that was a matrix, and you wanted to implement matrix multiplication, right? Like the cross product or the dot product or something. You could overload asterisks. So if you said vector A times vector, or matrix A times matrix B, you will get the dot product, because you overload it. So it's kind of neat. It also leads to some problems where people go, I have no idea what the equals sign means, right? But if you define it in here, and people are looking at your code, they'll see it. Here's what it does. Now, first of all, we have to get a couple terminology things here. Source is still the one you're passing in. This is the case where you say the following. You say int cell fixed C, semicolon. Remember what that does. That creates a box for C, and it has C's stored value, which points to that box, and it puts a 0 in there. OK? Now, you've got a C now that's created. If we went and said C gets B, OK, this invokes the operator overload for equals and says, oh, the compiler says, I have an int cell fixed over here, and I've got one over here, and I've overloaded equals so I can use the function that the user defined to do what I need to do. OK? So what it says is, first things first, int cell fig, which one is the source in this case? C gets B. This is the source. This one is the one that's getting the value. Guess what it's called? You can tell from up here. It's called this. Other languages have something similar to this, but I'm going to have to keep saying that word. Other languages have the construct I'm discussing, right? The variable here is called this. And it means the one that's getting copied into. OK? So you have to do a little check in here. Is it possible in C++ to say C gets C? That is totally legal C++. Why would you ever do that? Well, you never know why you'd do that. Right? It is legal to say something gets itself. There's nothing stopping you from doing that. In fact, maybe the compiler might do that sometimes when it's trying to optimize things. I don't know why, but maybe it would. OK? If you need to like waste a little time, maybe, I don't know. Whatever the case is, you're allowed to do that. If you try to do this in your equals overload, you're going to screw things are going to get screwed up. Because you're going to try to copy from one into another that already exists, and you're going to get into this weird problem. So the first thing you do is you say, if this is not equal to the source, if it's not C gets C, then we're OK, and we can try to do this function. OK? And by the way, this is a pointer to the variable, so you need to have the address of source to check if they're the same one. Okay? Now, all it's doing here is it's saying, OK, the value at stored value gets the value at source.stored value. I already have a box to put this in. C has already got a box. I don't need to create a new one. Now, be very careful with this. This code does not have an error, but it is misleading. You probably should do what to this box? If it was a whole array, and let's say that B had 20 values in it, and C had 1 value in it. This box would be, if it was an array, this box would be 1 big, and B's box would be 20 big. Is this one big enough to hold all 20 values? So really, you would want to delete this one, and then create a new one that's the right size. I skipped that in here, probably because I wasn't thinking about it, but that's really the better way to do this. In other words, don't use the location you've already got. Because you can, in this case, it works out because there's no way to make, we don't have a situation where stored value is ever more than 1. Otherwise, you would want to do that. But what this does is this says, OK, now copy the source's stored value into my stored value. So it changes this to be 2. And then, hold on, and then it returns this value. Notice, this is a function that has a return value of an int cell fixed. So guess what? You have to return something. You return this. Here's why. Has anybody ever seen the following in C++? A gets B gets C. Have you ever seen that? You're allowed to do that too. That means that C goes into B, which returns the same value which goes into A. So you have to return whatever you're copying here so that you could say C gets B gets A gets D, whatever. OK, you have to do that. It's another little piece. Question, Tafari? Oh, no. OK, if it comes back to you, raise your hand again. Anybody else on this? OK, so we now have written the 2 functions that we need to make this work properly. Let's just walk through it. OK, this is all the same as before. All right, int cell fixed A2. We create a box A. We put 2 in it right here. OK, we then call int cell B of A, which says, oh, this is the copy constructor. By the way, the reason this worked before is that the compiler built a copy constructor for you, but it didn't do the right thing. It basically said, OK, they didn't build one, but I know how to do that. And it just copied the values of the private variables, which happened to be the values were pointers, so it copied the address from one to the other. That's why you ended up with the problem. Yes? Did you figure it out?
Yes. I was going to ask, so if you do that, like, I guess the normal way without making no infrastructure, would it, like, if you had, like, an array, like, if you did this, but then, like, you had, like, int, and then, like, A, and then, like, in parentheses was an array of integers, would it make the new variable?
It would not make a new integer array for you. It would copy the address, so they would both be pointing to the same array. And then, when you go and delete one, you get a double free when you try to delete the other one. So that's what caused a bunch of double frees in your homeworks.
So it automatically is doing the pointer?
It automatically copies. It says, oh, all I know how to do is copy the values. And it can copy values just fine. It happens that stored value is a pointer, so it copies the address. It doesn't go into stored value and copy what's inside. I mean, it has no idea what's inside your vector or your array. It has no idea. So it can't go copying because it has no idea how big it is. It has no idea what's in there.
But I was thinking if it was actually like an array.
It would only copy the address. It would not copy anything inside the array. This wouldn't either, by the way, because we didn't have a for loop in here. We'll get to that. When we do the queue, we'll get to it. Question?
What's the point of the overload copy here? What can it do that the copy constructor?
It does it correctly where you get an actual, what we call a deep copy of the object. So remember when I said you can't say QA gets QB, because it ends up they both point to the same array, which is probably not what you want. You want an actual copy that has its own array. And that's what the point of this is for.
When would that capability be useful?
When you're trying to set two queues equal to each other, for instance, or whenever you're trying to set two objects equal to each other. Okay, you generally don't want the 4, 4, 4 solution. You want the 4, 2, 2 solution. When I say A set value 4, I only want A's value to change. I don't want B's and C's to change. This is generally what you want. Okay, and you also end up with memory leaks if you do this the wrong way anyway. Question?
So in the operator overload, you say star stored value gets the
Yep.
star.
Yep.
Or why don't you need to access this dot stored value?
That's a good question. You could say this dot stored value. That's fine. But because you are actually in this, you're in this, right? So you don't need to refer to it. But you do need to refer to it if you're trying to return it. Because how do you need to return yourself, so you better have a way of referring to yourself. Otherwise, you know all your own private things, right? Yeah, good question. OK, so we do this again. We get down here. We create A. We create a copy of A, which gets its own box to put 2, and it copies the 2 in there. Then we create C, which has a value of 0. We say C gets B, calls the operator overload, which copies B's value into C's box here, and it's 2. Then when you say A set value 4, it only changes A to 4. And therefore, when you print it out, it now prints 4, 2, 2. OK, Cornelia?
So, with the copy
Yay.
constructor, does the problem with the sizes not rise?
Does the problem with which?
Like where you should delete it and then delete it.
Well, in this case, you don't have to delete it because there's always only one value. So you can reuse the box.
But if there were,
If there were, you would have to do that. Let's hold off on your question. You'll see with the queue in 1 second when we do it. OK? So let's go to the queue here. This was from your homework that you all finished this last week, right? If we do this, if we set up the queue, and here's all the functions here, or the variables, and you say Q1, Q1, that will create a queue for you that has a queue array, pointer, and all these things. Then you do Q2, Q1, which says give me a copy of Q1 and make it into Q2. What that does is that says, OK, I know how to do this. I will copy the address here and give it to you as Q2's queue array, and then copy all these things. So it will be a working queue. But guess what? If you change anything, if you do any NQs in Q2, that also NQs in Q1. Probably not what you want. Same thing here. If you say Q3 gets Q1, you're creating a new Q3 variable that gets Q1. This will call the copy constructor because Q3 did not exist yet. Same thing. It will say, OK, Q3, I'll copy all the stuff. It copies the address, and you've got a problem. If you try to do Q4 and then Q4 gets Q1, which is really what a lot of you guys tried to do, then this will fail as well. Same idea. OK? So we have to create the copy constructor, and we have to create the other things. OK? We need what's called a deep copy versus a shallow copy. C++ on its own will do a shallow copy for you, meaning it will copy the values of all these just fine. It will not go into the queue array and copy all the values over from your queue. OK? That's what happens there. All right. So here's what we're going to do. I was going to make you guys do this. We do not have time right now. And it's not really worth doing in class. Here's the copy constructor. It's a bit more advanced than that one we saw for int cell. What do you have to do? You have to call a it's a constructor. It does not return a value. It has a const q reference called source. You set the sizes equal to each other. You basically say the size of the one I'm creating gets the source's size, capacity, same thing. Then you create a new array because you don't have one yet. Then you copy it. And this is the copy here where you copy source, front, I, blah, blah, blah. You do the exact copy. OK? In fact, this is not quite an exact copy, as it turns out. But this is the way you do it. OK? And then you set everybody else. this will make you a new queue and copy everything such that it has its own queue array. Okay? Don't write all this down now. It's on the slides. OK? Let's do the operator overload. Also looks kind of advanced. But guess what? It's not so bad. Remember, we have to check to see. This is called alias checking. In other words, you don't want to see if Q1 gets Q1. That would be bad if you tried to do all this business, because you'd immediately delete the one queue that you had, the array that you had. Right? Bad news. Why do we delete the queue array? Because Q1 already exists. When you say Q1 gets Q2, Q1 already exists. You better delete, clean up after it. Then you set all the things. This looks very similar to the copy constructor. Then you have to create the new array. This is exactly the same as well. And then you do the copying, one value at a time, and set the thing. And then you have to return an address of yourself. Yes? Sorry, an object of yourself.
Why you don't usually want to delete the queue immediately, but it's okay here?
You do want to delete it immediately.
Oh, okay.
That's,
You just said that you would do the one that you are using.
if you said Q1 gets Q1,
Okay.
if you forgot this line, you would then go and delete Q1's array, and then try to copy Q1's array into Q1's array, which doesn't exist anymore. Segfault city. OK? All right. OK. So now you've got this. Now, where are we going to use this? We're going to use this again in your homework 4, because you have to build a copy constructor, or at least an overload equals overload. If you have trouble with it, go back here and copy things exactly. This is not going to be a queue anymore. It's going to be a binary search tree. OK, this is going to be the same. This is going to be a binary search tree. Everything's going to be more or less identical. The only difference is you can't just copy a tree by going through the values. You have to walk through the whole tree, which you will practice in lab today and tomorrow. So in lab today and tomorrow, you will copy trees, or you will do you will not copy, you will traverse trees in 4 different ways. One of those ways is the destructor function, which will copy it do it in a post-order traversal, which means that you're going to basically traverse down and then delete the bottom one, the one you get to, or the one that you go get to. OK? Yes?
Sorry. So could you just use, so this is what I was trying to ask, I guess. Could you just after delete call the copy constructor?
You cannot call a constructor. You're not allowed.
Oh, okay.
Yep. You would think, oh, that's an easy way to do it. You're not allowed to call a copy constructor because more stuff is going on in the background. So you can't ever call a constructor yourself.
But you couldn't be like this.
You could create another helper function that does all this separately and pass it in the right values and all that if you wanted to. Yeah, you could. OK. All right. Question. Yeah, Tafari.
But isn't that, aren't you calling the constructor when you do equals?
No, when you say this, it looks like you're calling the constructor, but there's more going on than that. You're actually creating a queue, and this means, hey, I'm going to go call the constructor. But more stuff goes on in the background. OK? All right. That's overloading and copy constructing. Whew. OK? All right. Shake it out a little. Let's talk about balanced trees. So before, when we were talking about trees, we talked about this idea that sometimes trees can be degenerate. In other words, they can look like linked lists, right? They can look like a bad tree might be something like this. If I inserted even into a binary search tree, it could be bad. If I inserted, let's say, 4, and then I inserted 5, 5 would go where? To the right of 4. Then I inserted 6, and that has to go to the right of 5 and 6. And then I put 7 in there, and I put 8 in there. This looks like a degenerate tree, looks like a linked list, and not so great, right? So what we can do, what we need to be able to do is keep our tree balanced. Okay? Because when it's balanced, you get this logarithmic behavior because it's more or less split in 2 at every branch, and you can search through it logarithmically. Woohoo. Yeah?
Just wondering, does this mean that you always get that behavior if you try to pass into a tree, say, a sorted array?
Yeah, absolutely. If you tried to pass into a binary search tree that wasn't a special one we're going to talk about, you would get this behavior. Sure. Yep. Yep. You have to watch out for that sort of thing. Okay. Good question. So what we could do is we could turn this into a more balanced tree. How might we do that? Can you rearrange these so that it's more balanced? Yeah, I went on.
If like we weren't doing comp sci, 6 would be the
OK, if we weren't doing comp sci. Yes, we are doing comp sci, but OK, that's fine. And then what?
like if we didn't have like we were
OK.
in the computer, then the left would be 5.
5,
The left of that would be
4,
and then from 6 to 7, 8.
7, and 8. Were you going to say the same thing? No? OK. So this is more balanced. Now, it's kind of more balanced. Whoops. It's only gotten us, like, it's only helped out in one case. Right? It's only helped out at the root. Everybody else is now is still unbalanced. Right? So this is a balanced tree from the root's perspective, but not balanced from any other perspective. Right? So we got to do a little better than that. Because this only helps in that one case where you're going left or right at the root. Everybody else still looks like a linked list. Yeah?
But you have recursion.
Well, you do have recursion, but it doesn't really matter in terms of walking down this tree. If you're trying to search for 9, you go right, and then right, and then right, and then right. And you haven't broken the problem in half.
Do exactly the same thing for both subtrees.
Right, well, right. We are going to do something similar for the subtrees in the sense. But let's just say that now this is balanced from the root's perspective, but not in general. So far, so good? OK. Yeah.
The one up there with 6 at the top actually optimal for 5 ones? I mean, you can't actually have more branches on any individual number with only 5 values, right?
Yeah, I think this is pretty optimal for this. Although I suppose you could, yeah, that's pretty optimal for this. Yep, yep. You're not going to do better than this, but in general, you can get this. And if you had lots and lots, it would be bad. So yeah, yep. Do you have a question? No. OK. All right. So let's see how we might be able to do a little bit better. OK. You could insist that the entire thing is balanced. In other words, OK, everybody's balanced. Right? Insist that every node must have left and right subtrees the same height. This is actually a bit rigid in this case. OK? Because, first of all, you could only have a perfectly balanced tree with 2 to the k minus 1 nodes. Right? Otherwise, not much else you can do. Right? And not only that, it would be kind of painful to try to make that big, long tree we had over here, if it was really long enough, even if it's recursively, to rearrange everything in this case. You want to do better than this, but you can't get it perfect. OK? It's just too hard. It's too much work and not worth it. So let's make the condition a little less rigid. There were these 2 guys named Adelson Velsky and this other guy named Landis. And I guess Adelson Velsky got the better part of the name because he got 2 letters of his name, and the other guy only got 1. It's called an AVL tree. These guys said, OK, here's what we're going to do. We're going to make a binary search tree with the following invariant. The invariant is that for every node, the height of the left and right subtrees can differ by only one value, by only one length. OK? And we're going to say an empty tree has a height of -1 because it's just empty. OK? What that means in English, if you have a node, if you find the height of the left subtree and you find the height of the right subtree, they can differ by no more than 1. OK? So this one happens to be an AVL tree. Why? Because let's go from the bottom here. 3 has 0 children, so 0 and 0, its children are perfectly balanced. 4 has 1 on the left and 0 on the right, so it does not differ by more than 1. 2, 1, 2, and 1 means that it does not differ by more than 1. 5, 1, 2, 3, 1, 2 does not differ by more than 1. Let's see. Did I miss any? 8 and 7. 8, 1 and 0 does not differ by more than 1, and 0 and 0. That's an AVL tree. Yes.
Is it possible to have multiple possible AVL trees with the same combination of numbers? Like the one
Probably.
isn't an AVL tree, but it has the same set of.
Yeah. Yeah, I think so. Yeah, sure. No reason not to. Depends on how you insert them. Yeah, depends on how you insert them. OK, the one on the right is not an AVL tree. Can somebody tell me why? Somebody has an answer in a little bit. Yeah. Emil. Yeah, 7 has 1 and 1, 2, 3. Not balanced from an AVL perspective. OK? Let's look at the other ones. This one's fine. This one, 1, 2, 1. Yep. 1 and 1. Yep. 0, 0, 0, 0. Yep. 0, 0. So 7 is the only one here that's unbalanced. 2 and 4. What's wrong with 2 and 4? 2 has 1 on the left and 1, 2 on the right. In terms of the distance to the bottom, it's going to be only differ by 1. OK? All right. So let's see what we can do with this. So now we know. Yeah.
I don't know if it's a random question, but
OK.
can you potentially store a tree within one of the nodes of a tree?
Can you store a tree within one of the nodes? You kind of are in the sense, in a very recursive sense, right? The root of the tree defines the whole tree because you can follow its left and right down the path. So yeah, in some sense you do that. Yeah.
How can you guarantee something is going to be an AVL tree?
You can't. Well, you can by counting. You have to count, and you have to keep, in each one of these, we'll keep the height of its children.
But don't you then have to change stuff behind you if you're.
We'll see. Yeah, we'll have to make some changes. You'll see. You will see what kind of changes we make. So yes, we keep the height information for each node. Absolutely. And in practice, AVL trees are almost log n. They're only different by log n by 1 at most. Right? At every subtree, log n is guaranteed except by 1, which is great. It's still, in the big picture, logarithmic, OK, which is perfect. When we insert, though, here's what we do. It's a binary search tree. It happens to have more invariants. It's a binary search tree. And we basically just insert as if we were inserting into a binary search tree. Then we have to say, whoa, wait a minute. Maybe we've got to make some changes to make it go back into AVL form. OK? First things first. You have to start with an AVL tree in order to insert into an AVL tree and keep the property. You can't say, oh, it's not AVL now. I'll add some more stuff and make it AVL. It doesn't work that way. You have to change it you have to make sure it's AVL first. And then you can add one node. And then it's a relatively, definitely a keyword, relatively, simple process for reverting it to AVL status. OK? We have to maintain it. It is a little tricky. But what would we do? If we want to insert into this, let me write this one down. 5 and 8 and 7 and 2, 1, 4, and 3. If I want to insert 6 into this in a binary search tree, where is it going to go? Yeah, Janelle. Left of 6. Now, is this now an AVL tree? It's not anymore because of which node? What's the first one going from the bottom? Which one's the first one that has a problem? 8 has a problem. OK? As it turns out, you're only going to have to go up and fix 1, and the rest of the tree is fine, which is actually kind of clever. Right? It's very cool that you only have to change 1, and then the rest of the tree is absolutely fine. Yeah?
So could you then switch the position 7 and 8 and make it so that it stays AVL?
We're actually going to do exactly that. We are going to make sure it stays AVL. We'll see how in a minute. OK? That's almost the way we're going to do it. But we're going to formalize it a bit more. OK? All right. What we're going to do is this thing called a rotation. In other words, we're going to perform an operation on this tree at the node that's got the problem, which in this case is 8 if we add 6 in here. OK? We're going to do an operation where we rotate that in the direction that would make it balanced again. OK? So only nodes on the path from insertion really make their balance, have their balance altered. If I insert to the right-hand side of this tree, there is no way the left-hand side becomes unbalanced. It just it's not possible. So if I insert over here, then this side's the one I'm going to work at. And you go from the one you insert back up the tree until you get to a point where it's unbalanced. Okay? Here's how we do it. Well, here's some information about that. Nodes only have at most 2 children. So there's only 4 different cases of inserting where it's going to be different. And it turns out that the cases are absolutely symmetrical. So really, there's only 2 cases that are symmetrical. You will see what I mean in a second. You could insert into the left subtree of the left child of some node. 8 had the problem after we inserted 6. Notice that 6 is in the left subtree of the left child of 7, or of 8. The left child of 8 is 7. The left subtree is where it went. That's case 1. Case 2 is the right subtree of the left child. Let's say we inserted 7.5 into here. Where would 7.5 go? If go here, notice that 7.5, 8 is still the one with the problem. 0 here, 1, 2 here. So we inserted 7.5 into the left tree, or the left subtree, or I guess left child, but it's right subtree. So it's the right subtree of the left child. Left child, right subtree. Okay? What if we instead had inserted, let's see what another example is. Let's say that we had 10 in here, and we inserted 9. 9 would go here, and this would be the right child's left subtree. The left subtree of the right child. Okay? If we inserted 11, we would go into the right subtree of the right child. Good? OK, there's the 4 cases. Turns out that they're exactly symmetrical. The left subtree of the left child is symmetrical to the right subchild of the right subtree of the right child. So we only have to worry about 2 different cases. Let's talk about those cases. For the outside cases, left, left, right, right, it turns out we can do what's called a single rotation. And I'll show you what that is. For the inside cases, that's the other 2, left, right, and right, left, we have to do a double rotation. We will not get to a double rotation today. We'll do that on Wednesday. It's the single rotation that we have to worry about right now. Okay? So let's think about it. Sometimes I think this isn't that clear. Circles are nodes. Triangles are subtrees. Basically, you can kind of think of them as nodes, but in the sense of the size of these subtrees doesn't really matter, except they have to differ only by 1 and 2, like 2 there. Okay? That's all this really means. But what happens here, let's take a look at this one right here. Let's look at inserting 6 in here. We said that 8 is the one that has the problem, because we inserted 6, and now 7's fine because it's not differ by more than 1 and 0. And 8 is 1, 2, and 0, which is the problem. Which way should we shift 8, left or right, to balance this little subtree? We shift it this way. OK, I will show you how to do that in a second. But basically, we're going to want the following result. We're going to want 5. It's going to end up being 7, 8, 6. And then this one stays the same. 2, 4, 3, and 1. OK? We're going to try to go from this to this by shifting 8 to the right, like this. OK? This is basically the idea. If we end up moving, if this is the one that's the problem because it's 1 and 1, 2, 3, then, because this is actually a double size, 1 and 1, 2, 3. If we shift k2 over, we can end up being k1 at the root, k2 being here. What's the relationship between z and everything in z subtree for k2? Everything in z has to be what compared to k2? Greater. Everything in k1 has to be what to k2? Less. Everything in y related to k1, greater. So if we have k1 here, then if we move k1 up here, k2 is going to be the next biggest. Okay? And then underneath that, on the left, is going to be the next biggest for y, which is bigger than k2. We said y is, or sorry, less than k2. Y is less than k2. And then to the right is the things that are bigger than k2. Okay, this is what it looks like. Here's how you actually do it. You grab the one that's the one, so we're trying to rotate k2 this way. You grab the one next to it, and you pull it up and shake it. If you shake it, if you pull k1 and shake it, what happens is it ends up where if you shake it up here, k2 is the next, like the big next one you want to kind of fall down the little tree that you've shaken now, and it ends up putting k2 here and z here. Let's see what that looks like on the one over here. 8 is the one we want to rotate this way. We're going to grab the one on the other side of it, and we're going to hold it up and go whoop and shake it. And that's going to replace this one here. So in other words, we're going to shake 7, and the 8 is bigger than 7, so it's over here, and the 6 is less than 7. Do you see how that works? Okay, it ends up working out just fine when you have bigger trees. The exact opposite is true. Well, this is exactly what we just did. Now, notice, once we fix that, right, it actually, well, nothing else broke, but it would have fixed anything else above it that was also broken. Okay? Turns out it's exactly the same if you go the other direction. K1 is the one that's the problem here. We're going to rotate K1 this way, which means we grab onto K2 and shake it. And the way it shakes out is, well, the only thing that's bigger than K2 is Z. K1 is the next biggest thing that we can, well, is the one that we're basically not going to, we're not going to slide K1 down. We're basically going to take whatever K2's left child is and put it to the right of K1. Okay, and then this ends up balanced. Okay, now, I know that was a lot of like stuff really quickly. Let's actually do this on a demonstration. I'm going to write some of the ones down. 3, 2, 1, 4, 5, 6, 7. 3, 2, 1, 4, 5, 6, 7. You'd think I'd be able to remember that. So you guys know that it's E-Week. I don't know if you knew that's E-Week, Engineering Week or whatever. So there's this contest for professors that's about memorizing the digits of pi. And somebody roped me into it. So I have to memorize a whole bunch of digits of pi, and I'm not necessarily looking forward to it. How many do you think I'll need to get to beat all the other professors? 100? I'm doing at least 100, trust me. How about like 200 or 300? Yeah. At least 100. OK, so we're going to check this out. There is a website that you can go to that will allow you to see this visually, which is awesome. You should definitely write this website down. It's on the slides. Go to the website here. Here's what I'm going to do. I'm going to start to insert these things. And you can change the speed, and you can change various parts of it. I'm going to insert 3. When I insert 3 into a tree, OK, it does this. It just puts 3 there. OK, sorry, it's a little hard to see on the screen. Let me do this. There we go. OK, so I'm going to insert. I inserted 3. Now I'm going to insert 4. Where's it going to go? Sorry, 2. Where's 2 going to go? 2 is going to go to the left. And what it's going to do is it's going to do it, and it's going to walk through and check the levels. And notice the levels are actually drawn on here. OK, 1 and 2. OK, so for here, 0. So this is like 1 down here and 0 here. OK, I'm not sure why. I think this is the height of each one. OK, let's insert 1. Where's 1 going to go? To the left. Is that going to screw anybody up? Which one? 3. So we're going to end up, watch this. I will put 1 in, and then I'll pause it when it gets down there. And we'll just walk through what's going to happen. OK? We're going to do 1. We go up here. This is fine because it's 0, 0. This is fine because it's 1, 0. This one is not fine because it's 1, 2, 0. What do we want to rotate 3 which direction? To the right. Which one do we grab? 2. Shake it. 3 ends up over here. 1 ends up there. And it will be fine. Okay? And it's a nice little animation. Now, let's do 4. How about 4? Where's 4 going to go? 4 is going to go to the right of 3. Is that going to screw anybody up? No. Everybody's going to be fine. Okay? It's going to go up and check, and everybody's fine. If we insert 5, 5 is going to go to the right of 4. Who's going to get screwed up? By the way, both 3 and 2 are screwed up, right? 3 is screwed up because it's 1, 2, and 0. 2 is screwed up because it's 1, 2, 3, and 1. But once we fix 3, it will solve 2's problem. Watch. 3, 2. So that's the one that actually got rotated. Because 3 was the first one. We grabbed 4. We shook it. Good to go. OK? How about, let's see, we just put 4 in there. We just put 5 in there. How about 6? 6 is going to go into the right of 5. Is anybody going to get screwed up? Yeah, which one? Let's look. 4, 1, and 1, 2. We're fine. 6 is 0, 0, 0, fine. 5, 1, 0, fine. 4, 1, 1, 2, fine. 2, 1, 2, 3, 1. So you have to go all the way up to 2. Which way is 2 going to rotate? To the left. We're going to grab onto 4. OK? And then 4 is going to be shaken up. 2 is going to go to the left of 4. We're going to have to fit 3. And where's 3 going to go in relation to 2? To the right of 2. OK? So like this. 2 is the one that gets rotated. Grab 4 and go whoop like that. OK? And now everybody's balanced. One more. 7. Is 7 going to screw anybody up? Which one? Let's see. 7 is going to go in, and it's going to screw 5 up. So you're going to rotate it which way? 5 is going to rotate left, so you grab 6, and you hoist it up 5. So it goes 6, 5, 7, and 4. And we are then good to go. There we go. And it grabs it, and bing, like that. OK? That is a pretty cool thing. So if you get confused about it, go ahead and ask. Yeah?
So if there's a program that doesn't keep count of how many of each individual number you have, and you're to try and insert 6 into here,
Yeah.
where would it go to the right of 6 or to the left?
It's up to you.
Okay.
It would be hard to do this with an AVL tree, I'm guessing. Yeah. Yeah.
Can you try an inside case?
Can you what?
Can you try an inside case?
We'll do that later, on Wednesday. We got to do the inside case on Wednesday. You can look at the notes if you want to get a little thing. But yeah. Yeah.
Doesn't this require some sort of double linking? I'm just looking at how it would be implemented.
Does this require double linking? Yeah, you definitely want to keep like parent pointers in this case. Yeah, you'd have to keep some parent pointers. Yeah. OK, any other questions? You will practice trees on lab tonight and tomorrow, and I'll see you Wednesday.